बिस्मिल्लाहिर्रहमानिर्रहीम। डियर स्टूडेंट्स, अस्सलामु अलैकुम। मैं आपको आज ग्रुप थ्योरी के इस ऑनलाइन लेक्चर में वेलकम करता हूँ। उम्मीद करता हूँ आप सब लोग खैरियत से होंगे। इससे पहले हमने दो लेक्चर्स जो हैं वो देखे हैं ऑनलाइन, जिसमें के बात की गई है ग्रुप्स ऑफ परम्यूटेशंस की। So let's quickly revise what we did in the last two classes. A permutation is a bijective mapping from a set to itself. Bijective mapping means it's one-to-one and onto mapping. And we have seen from a set having n elements, there could be n factorial bijections that can be defined on that set. And one more fact we have discussed: if we collect all the permutations defined on a set, then these permutations forms a group under the operation of the composition of mappings. आज हमने इस लेक्चर में कुछ क्वेश्चंस करने हैं एक्सरसाइज के, जो टेक्स्ट हम फॉलो कर रहे हैं जॉन बी फ्राले की बुक जो फॉलो की जा रही है, और उसकी एक्सरसाइज 8 पे हम फोकस करेंगे। जो लेक्चर का मटेरियल है वो ऑलरेडी गूगल क्लासरूम पे शेयर हो चुका है, तो लिहाजा अब हम वहीं से अपने मटेरियल को लेते हैं और क्वेश्चंस को सॉल्व करने की कोशिश करते हैं। ओके, this is our Google Classroom for the course Group Theory for BS Mathematics 5th semester, and this is the code to join this classroom 6HECU4N. So we already have 26 students added in this Google Classroom. So आज का जो हमारा फोकस है वो इस एक्सरसाइज के क्वेश्चंस को सॉल्व करना है। So let me open this. So we need to wait a little bit. So the first slide is going to be open. So I think all of you can see this slide. So the text which we are following, Abstract Algebra by John B. Fraley, page 83, exercise 8. So in first 5 exercises, we need to compute the indicated product involving the following permutations in S6. Okay. आप लोगों को मैंने दो परम्यूटेशंस को कंपोज करना बताया है। कंपोजिशन को यहाँ हम प्रोडक्ट भी कह रहे हैं, प्रोडक्ट ऑफ टू permutations. So if you recall the previous lecture, of course for S6 the ground set is the set A having 6 elements, 1, 2 up to so on 6. And by rule I told you if a set has n element, then there are n factorial permutations that can be defined on that set. So according to that, there are 6 factorial, means 720 permutations that can be defined on this set A. Out of those 720 permutations, we are given 3 permutations: sigma, tau, and mu. So for sigma, you can see the geometric view or the diagram which I told you earlier is here to facilitate you. So 1 is mapped on 3 under sigma, 2 is connected with 1, 3 is mapped on 4, 4 is mapped on 5, 5 is mapped on 6, and 6 is mapped onto 2. So you could also write in this way, image of 1 under sigma is 3. So you see sigma applied on 1 gives you the image 3. So 1 is connected with 3. Similarly, if you look at the last entry, 6 is connected with 2. So this is a 1-to-1 and onto mapping. So of course, this is a permutation on the set A. So 1 is mapped onto 3, 2 is mapped onto 1, 3 is connected with 4, 4 is connected with 5, 5 is connected with 6, and the image of 6 is 1 under sigma. So this is the same sigma in this diagram as written over here in the form of an array. So sigma is 1, 1 and on 2. Of course, sigma is a permutation. So sigma from A to A is a bijective mapping. And similarly, tau and mu, they can be represented in this way. So we need to multiply these permutations according to the situations given. And in the last lecture, we have seen there are actually 2 ways to take composition of 2 mappings, and we are going to follow our text in which the input is on the right hand side and we move from right to left. So to compose tau and sigma, first sigma will be applied on x and you will get the result as sigma of x, and then on this output we will apply tau to get the final output after the composition. So tau times sigma. In the last class, I gave you the direct way to multiply, which is written over here on the right hand side of this slide. But actually, if you want to see the details, they are given on the left hand side. So what is happening under this composition is explained by applying on each and every element of the set A. So we could have 6 inputs because the set A contains 6 elements. So tau sigma or tau composed with sigma, you could also write some circle sign here, but sometimes we don't write this circle, just you could write the tau dot sigma applied on 1. So this is a composed mapping. So according to this rule, first sigma will be applied on 1. So tau of sigma of 1. Sigma जब 1 पे अप्लाई हो रहा है तो आप देखिए sigma 1 पे अप्लाई होके आंसर 3 देगा. सो यहाँ पे बनेगा 3. इसके बाद अब tau की बारी है. tau जब 3 पे अप्लाई होगा, look at this tau. tau जब 3 पे अप्लाई होगा तो फाइनल रिजल्ट क्या है 1. So we see when we apply this tau sigma, this composition mapping on the element 1, we get the element 1. Similarly, we apply tau sigma on 2. So tau applied on sigma of 2. So sigma of 2 is 1. So tau will be applied on 1. So tau on 1 gives you 2. And similarly, you could compute all these products. Let me show you this case. Tau sigma applied on 4. First sigma will be applied on 4. Sigma will be applied on 4. You will get 5. It's the turn of tau to be applied on 5. When tau applied on 5 gives you 6. Tau applied on 5 gives you 6. So the final result is 6. So when you apply this composition mapping tau sigma on the input 4, you get output as 6. Now you see this is a very long procedure. You give input each and every element of the set A from 1 to 6, and then you generate these 6 outputs. Of course, these 6 outputs are from the same set A, as this is a permutation, and that is a bijective mapping from a set onto itself. We will not follow this lengthy calculation or computational procedure to compute the product or composition of mappings. Rather, we will follow the same simple rule that I gave you in the last lecture. So look at this. Tau applied on sigma. So first, this is the permutation tau. This is permutation sigma. And we will move from right to left, because here I have explained first sigma will be applied on each of these inputs, and then on the outputs given by the sigma, tau will be applied to get final output after the composition, and that is given here. Tau times sigma, you have given these 6 inputs, 1, 2, 3, 4, 5, 6, that are given in these brackets, and the second row corresponds to the output values 1, 2, 3, 6, 5, 4, 1, 2, 3, 6, 5, 4, and you will be getting same result by this short way of multiplication of 2 permutations. So be with me. 1 goes to 3, 3 goes to 1. So finally we will have 1. Now we need to find what is the image of 2 under this composition mapping. So 2 goes to 1, 1 goes to 2. So finally we will be having 2. Let us compute some other entry. 6. For this 6, I want to see what is the image. At the moment, we see a blank here. Keep in mind there is some blank, some box here, and we compute this entry in the box. 6 goes to 2 under sigma, and 2 goes to 4 under tau. So finally, 6 will be going to 4 after this composition. Now you see these two results are 100% the same. So we will be following this rule of multiplication from right to left, and by this short computational procedure, rather than by moving in this way, by giving all the inputs to the composition mapping and waiting what is gonna be the output. So this is very simple procedure to compute mappings compositions. So now we are ready to move towards next slide. So again, from Google Classroom, we take the second slide. Now question 5. So you are advised to solve question 2, 3, and 4 by yourselves. Now in question 5, we need to compute product of 3 permutations, sigma inverse, tau, sigma. You see on the previous slide, sigma and tau are given, but sigma inverse is not given. So first we need to compute inverse of the permutation sigma. Again, for this inverse, you can watch my previous video. So sigma is defined in this way in the problem. So to compute sigma inverse, actually we need another permutation that composed with sigma gives you the identity permutation. So if you look at the 7 factorial, means 720 possibilities, a hit and trial method would be you multiply this sigma one by one to all those entries in the set S6. And when you hit the identity permutation, so that would be the inverse of this sigma. But again, we will be having some short procedure to compute sigma inverse. So Remember from my last video, there is some intermediate step to compute sigma inverse. Just flip these rows, swap these two rows. This first row becomes the second row, and second row becomes the first row, and then the inverse of sigma would be obtained from this intermediate step just by arranging the letters. So first we will take this pair 1, 2 and we will set at first position. Then we will take 2 with the image 6 at the second position, and so forth. 3 with 1, then 4 with 3. So you have to arrange in this way 1, 2, 3, 4, 5, 6. So actually this is the inverse of the permutation sigma. So I warned you that you will not take this as inverse. This is some intermediate step. We need to then arrange all these entries from 1 to the increasing order till the final value. So simple check. If this inverse is correct, then sigma composed with sigma inverse will give you the identity permutation. You can see sigma, and then this is sigma inverse. We will move from right to left. First write 1, 2, 6, all these inputs. We want to see what is the output for these 6 inputs under this composition sigma inverse. So 1 goes to 2, 2 goes to 1. So finally we have 1. 2 is mapped onto 6, 6 is mapped onto 2, and so forth. You see, this gives you the identity permutation. Okay, we have all the ingredients to solve this problem. Sigma inverse was not given. We ourselves computed sigma inverse. Tau and sigma are given, so you write sigma inverse in between tau and then sigma. Now you have seen, since the set S6 is a group, so associative law must be there. So it doesn't matter whether you multiply these two first and the result is going to be composed with this, or you multiply these two first and then the result will be composed with the left one, and then you'll get same result. Okay, what we are going to do, this sigma inverse we leave as it is, and we see the output of the composition of these two. So first write 1, 2, 3, 4, 5, 6 here, and then we want to see what are the images. So 1 goes to 3, 3 goes to 1, finally is 1, 2 goes to 1, 1 goes to 2, we have 2, 3 goes to 4, 4 goes to 3, and so forth. Now you can multiply these two permutations and you get this as the final result. Okay, I hope the message is clear now. So we move towards the next question. The third slide from Google Classroom is this. So question 6. Please understand this question very carefully. I told you in the classes at our campus. Understand this notation. So we want to compute the order of the subgroup generated by sigma. So we want to see the span of sigma and then its order. So first we compute the subgroup generated by sigma. So this is sigma. We multiply sigma with itself. We get sigma square. Multiplication is already done on the previous slide. Then you compute sigma cube. You multiply sigma with sigma square. You get sigma cube. Then you compute sigma 4. Either by multiplying sigma by sigma cube, or you can multiply sigma square with sigma square. You will get sigma 4. Similarly, you compute sigma 5, and then you compute sigma 6. In sigma 6, what you see, this is the identity permutation. So we stop our multiplication here because after this, you will get repetition in these elements. So sigma 6 ने आपको आइडेंटिटी परम्यूटेशन दिया है, लिहाजा हम यहाँ पे अपनी मल्टीप्लिकेशन को रोक देंगे, बिकॉज इसके बाद जो सिग्मा 7 है एक्चुअली वो सिग्मा बन जाएगा. तो सिग्मा 8 है वो सिग्मा स्क्वायर बन जाएगा. So the group generated by sigma contains sigma. Of course, sigma is the generator for this subgroup. Then sigma square, sigma cube, all the way to sigma 6, which is the identity of this group. So this is a group generated by sigma. So this is a cyclic group, and we have to tell the order of this group, which is 6. And we have seen the order of a subgroup is the same as the order of the generator. So sigma का जो order है वो actually 6 है, क्योंकि sigma power 6 ने आपको identity दिया है. तो मैंने इस question 6 में आपको दो चीजें बता दी हैं. एक तो ये कि किसी परमुटेशन का ऑर्डर कैसे कंप्यूट करते हैं, आप उस परमुटेशन की पावर्स कंप्यूट करते जाएं till you hit the identity permutation. The same procedure we did in general groups. When you have a group, some element A from the group, if you get A to the power n equals to E, where n is the least positive integer, we declare that n is the order of that element. Question 7 on same lines you could solve, and I would like to wind up this lecture at question 8. We need to compute sigma to the power 100. And this is the same sigma we have seen here. So we calculated sigma power 6 equals to I. So we will break this 100 into this way, sigma 96 into sigma power 4. And sigma 96 actually is sigma 6 to the power 16. So this is identity element. Identity raised to the power 16 gives you again the identity permutation. So what is left is only sigma 4. This is the same situation, and sigma 4 you can see from here, this is sigma 4. So just write here sigma 4. So sigma 100 is actually sigma 4, which is equals to this. This is same situation like if you were asked to find iota power 100, you could write iota power 4 whole power 25. So iota power 4 is 1. 1 to the power 25 gives you again the 1. So I am going to wind up this lecture, and I will be coming in the next lecture with some new topic. Okay, my dear students, Allah Hafiz.